Good morning, and thank you for being here with us today. This is a job I made with Eduardo Garcia Pardo. This is something we created when we were at the university, Polytechnic University of Madrid. Now I'm working at Universidad Carlos III, and he's working Universidad Rey Juan Carlos as part of a cybersecurity project funded by the European Union. So I am a software engineer by the Polytechnic University of Madrid. I'm studying a master's degree in cybersecurity and Universidad Carlos III. I'm a security analyst in Línea Directa. I'm interested in analysis, anti-analysis, and malware detection, and you have my address. This is an abstract of the paper. I'm not going to read this, but at least you got the slide. So in this presentation, we will be talking about malware detection with artificial networks, something that has been discussed. So the use of neuronal networks, machine learning, etc. And the results might be weak, and these results are not known by the public. So we are going to research the state of the art of this kind of detectors. We are going to see how samples might be modified to evade this kind of techniques, and how to improve or help to improve their efficiency. First of all, an introduction of the basic concepts, then goals of our paper, and then I'm going to talk about the results and the conclusions and some action lines for the future. So, in introduction, we're going to talk about artificial neuronal networks, adversary examples, which will allow us to establish the framework. So what is the problem? The initial problem is that there are so many malicious software or malware that increase in terms of number of samples and complexity. Return of investment in cybercrime is huge, so the problems are even bigger. So the traditional detection elements to solve the problems were grouped into main sets. First of all, signature based traditional detection methods, sample equipment networks, and the other group of techniques are the heuristic techniques based on a group of rules established by an analyst, or things that might indicate that this is a malware or suspicious malware that could be applied statically with properties on samples, or dynamically, which are the characteristics in the execution times, for example, or behavior. The problem with these kind of techniques is they require prior analysis of the sample to establish firms or to know the heuristic part, and they require the work of an analyst knowing these heuristic techniques, even if analysts work, probably they're not aware of something similar. So this is automatic learning, which is machine learning. So they are based on statistics. The advantage is they learn on their own. So I say on their own in inverted commas because they are not autonomous, but they don't need pre-established rules established by an analyst. So following examples, the machine learns classifications and entries. So the idea is to be able to detect unseen malware, because the number of malwares increases every year. So what happens? Is this magic? Artificial intelligence, everything is good. What happens? First of all, these are techniques that are classified between artificial intelligence, within, that's what I meant, artificial intelligence. So artificial neuronal network or deep learning, which are big networks with many layers, so that's why deep. So this is a group of neurons connected to each other. So the typical thing is to have an entry layer. This is what we want to classify, and then an outlet or exit layer that is the result of the classification. Is this malware or not? And now, looking at this more detail, is that in each neuron we have the addition of all the entries mathematically. So this is the connection with other neurons, or the entry. X represents the value of the connection, and W is the weight of the connection, meaning if this connection is strong or not, and this is important for the final result. So this addition, which has also a B variable, so each neuron and how excitable they are, how reactive they are to entries. So we apply a mathematical formula to get a result and the different functions depending on the type of neuron. So there are modifiable parameters that are trainable parameters. So neurons can learn how to classify things. I mentioned entry layers, but what do they get actually? Well, the literature says that inputs or API calls or execution or images or bytes or binaries, images can also be gotten. But one of the most important trends over the last years is getting bytes, raw bytes of the samples, without getting the samples, without extraction of the characteristics priorly, so prior to their entries. So we can get rid of this prior extraction layer that might have errors used by analysts, challenges, because some of the samples are not labeled. So we make the entire binary to go through and the exit. And so if the exit is between 0 and 1, 0 malware, 100% security, this is malware. So an example, state-of-the-art used by the literature is malconv, represented recently, which receives a binary raw byte with an embedded layer that eliminates the semantic relationship between bytes with similar bytes on the same section, but then from different instructions that are not necessarily connected to each other. So two convolutional layers are applied, and then two layers, and then so the value between 0 and 1 to know legitimate or malicious. I'm showing you the structure of this layer because later on during the evaluation phase, I'm going to show you that we use this. So machine learning is not a final solution. I guess you know this already. This is not going to make our problems disappear, and it can be evaded. That's why we worked on that. But it's a useful methodology, especially for deep defense, heuristic approaches or holistic approach and machine learning. So what are the weaknesses of this kind of approaches, and why they are not going to make all the problems disappear? Because they are based on statistics, and because they learn from example, it means that we assume that the distribution of training data is similar to the distribution that we will have in a real environment. So what we'll learn to the network is not the same. They are fine because the adversaries will be motivated trying to detect something that has not been detected, so we are breaking the function. So the literature, this is called adversarial examples. This is defined like inputs to machine learning models that an attacker has intentionally designed to cause the model to make a mistake when classifying an entry. So these are optical illusions, but for machine learning. So on the example, we have two images that might be similar. One of them is classified as a panda, and the other one is a gibbon monkey. The only difference between these two images, which are similar, is a group of perturbations that were intruders, and the neural network classified them differently. When analyzing attacks, different approaches can be taken depending on the knowledge of the attacking of the neural network. So we will have a black box or a white box. White box, we have access to the model to be evaded and the structure. Black box, we have not access, but we can interact. So we can
different situations. One is we can interact with this, but we get on labels that's malicious or not. So the most difficult case to solve regarding the attack. Let's have some examples. The first situation, black box. We have these examples, they are common examples. Here we see one case. A module of machine learning prediction. The probability that a file is a threat. Predictive machine learning details. This neuronal network think it's malicious attack. There are several attacks where they say, well, it's due to machine learning, or even the probability of being malicious. This type of attack can be established trial and error, proving something where we have no access to. It is like before, when samples were uploaded to see if they were detected or not, and to try to evade neuronal networks. Nevertheless, this is different now. This is not so simple. The example I've given in front of you with the identification of images, the only problem is that it shouldn't be, the difference shouldn't be perceptible for the human being, shouldn't be knowledgeable. We see here some perturbations that are not easy to detect. The format we're going to see here, it is the double execution Windows format, where we have a most common format while getting or facing the malicious attacks. And it means there are two differentiated parts. On the one hand, the headers, where we have the metadata, and the compilation time, imports, exports, sections, subsystems, and then we have also the sections of the file, and then we have here the codes and data, the sections from the binary file that's going to be executed, what has been introduced by the programmer. And we have here, when there is the compiling process, we write the source code that goes into the executable format. This is the compiling process, and we have a lack of information here. If all the instructions we have from the source code, it's not seen in the case of binary code. We have here with the binary code to deassemble things. And we have here, it is easier for the analyst to see what can be done, to analyze the sample and to construct the flow control and to perform some analysis. The problem we have here is that this conversion, due to the lack of information, is not direct, it's not reliable. So we have to cope with some challenges, like finding data within the code, trying to have self-modifying codes. In the case of malicious codes, it's packed, so it's difficult to execute them. We have here some limitations, and it's a big problem, and we have here nevertheless possibilities of disassembling things. Evading malware detection is the name of our paper, so we try to cope with those limitations. Let's have three possibilities. The state-of-the-art possibilities to cope with the challenges, how to evade this. On the one hand, we have the Colosani et al. Approach. We modify what there is, we modify the references to the code that are been referred to. It's adding a section. You've analyzed this basic technique before. The problem is that those perturbations, those modifications are limited to a region, which is the less important one, because the one you are far from the header, you don't have important or reliable or important information, so neural networks do not expect a lot of information. The second approach is to use code caves. It's the alignment of sections alignments. We see the way they manage the space that is very limited and not recognizable. If you have 12 bytes and it occupies 500, you introduce 12 bytes to reach the size which is just filling bytes. When you upload the sections and you have the mapping, the virtual memory and the physical memory, the movement should be a full block, and it's faster. So we have here problems. The space is limited, very limited, and the advantage is that it is not easy to recognize. You don't know to what extent we're having trash or we're talking about perturbations or modifications. Another thing is to change instructions by something that looks like. So it's semantically alike. Two instructions after the execution will give the same state. You can replace one from another, and the execution time is not important, not for us to consider. So when you introduce this mechanism, this approach, we're assuming that the code cannot be self-modified. We're not going to modify the code, the execution time, to generate another code, because they look alike, they're semantically the same, but the bytes are not the same. So it's difficult to detect, not impossible, because those are uncommon instructions, and the compiler haven't decided, you have decided, so the space is limited, and of course the code is something recognizable. So I've mentioned the introduction. Now you have some ideas, objectives and restrictions. Well, they were going to say, what is this guy talking about? What are we going to do? Well, it is the deep learning malware detection. The title is nice. We have talking about deep learning. Deep learning is something that sells good, but what are we going to do with the deep learning? Evading deep learning malware detections. We're going to talk about improving the effectiveness of the malware detection based on the, RNA. So we are going to help those fighting against it. So we have going to enhance robustness, and we're going to propose a method generating examples to assess how robust they are, and to train us neuronal networks with those samples to improve and to have robust networks. Restrictions, first of all, this is a black box mechanism allowing us to assess, to evaluate without changing mechanisms, without knowing the model we're going to assess. It is one size fits all. If it works on bytes, and then on the other hand, we're going to have a binary approach. We do not have access to the source code. So we have here malware writers won't give us their debugging aspects, and we want the samples to be functionals. The evasive samples should be behaving the same as the functional samples. We have here optimizing as a problem. We have entry Z, and we have epsilon is the limit, and we consider that's the ceiling dividing the malicious samples from not the malicious one. And we have here the entry is zeta. We have 8.5, and we want to have a sample zeta prime with an entry that will be lower than this threshold of detection. Threshold means this evasion belongs to M set, and the malicious samples will behave like the original ones, and we haven't got access to the fire function. We have here two parts. First of all, how to introduce the perturbation, and on the other hand, how to optimize what we've used to make this happen, to have the best possible approach to evade detection. So the question is, we have a very sensitive format, and we have corruption when there are changes. We have challenges when disassemble things, but the memory structure can be modified, because can we modify the file without modifying the memory structure? We have to consider the loading process in Windows operating systems. As I said before, in the headers we have section tables containing information on the file section, telling things like the address within the file, the size per section, and the direction of the memory, the address of the memory, sorry. When we have here the operating system, they reserve necessary space to allocate them, and they copy this in this space, on the space, and they convey control and execution. My question is, if we modify the headers and we make the addresses to point towards another space, will these be respected by the operating system, or will they take a part of the next section, the beginning of the next section? Perhaps it's not the way it's been modified. If we introduce modifications and if we disturb this, the original sample is on top. There are two sections, and one that does not occupy disk space, but it is mapped exactly like the one that is down there, which is a modified sample. We have introduced modifications that are not typified, but they're mapped. So we have introduced modifications, perturbations with the limitation of space in different sections of the file without concerning the memory structure. So we respect the original function, the original coding case. And we have the binary we want to evade. It is bigger and it is detectable. We're introducing modifications. What the hell are we doing? So we know that that's no problem, and we'll see why this is not a problem. So we've introduced modifications, but this cannot be so simple. We cannot introduce 3 blocks and to evade the whole thing. So what we have here is a process of optimization. We have to modify perturbations we have introduced to find those that will allow us to evade the problem. And so we have 3 limitations. We don't know the optimal number of bytes. That's something we do not know. The number that will give us the best prediction, and we don't know what to introduce. We haven't got guidelines. We don't know where to do or what the higher probability is of being accepted. And then the ideal modifications differ by binary, because each binary file is different. We're going to introduce perturbations, modifications that will be different per different section. Ideal perturbations are differing from per block within the same file. What does it mean? It is not the same to introduce this prior to the code section or prior to the data section, because that does not mean the same in the case of neuronal networks. So to solve the problem, we have to use one of the algorithms, the common algorithms, while finding solutions. And we don't know if this is going to be the best solution or not, but we need fast solutions. Those are genetic algorithms introduced by John Holland back in the 60s, 70s, and a PhD student made this as a subset of the meta-heuristic algorithms based on evolution theory. Neuronal networks are inspired, in the case of neurons, the brain structure. Genetic algorithms are based on Darwin approach and how we have mutations to improve populations. And the theory is that we construct a solution population. We call solution each sample, evasive sample from the original created. If we have 50 different modifications from the original sample, each one is a solution. 50 solutions then, that's a population of solutions. We assess solutions with the objective function, which is the prediction we get from neuronal networks. And then we have a process of optimization, which is selecting individuals. We cross them and we mutate the genetic load of the children. That's the next generation. And we optimize and optimize till the new generation will have the same individuals as the original population. The selection process is such that solution, the strongest solution, the most adapted solution will have probability of being part of the children more than the less adapted case. And then we get this top condition. It is a solution satisfying our needs, or we take for granted that it won't be possible, acceptable period of time. We have 100 generations iterating, modifying the sample, and we haven't improved to more than 0.001. So we say it's impossible, we're not going to have it, and we're going to modify, we're going to the next one. In order to generate this genetic approach, we need convergence ratio. It is from the observation till exploitation. We have to have a convergency, and this should be proportional to the pressure, identifying the strongest individual able to reproduce himself. So this is a problem while solving the local optimal cases. When we talk about exploration, we talk about distribution of solutions all over the space. So finding regions that are promising, where the solution, the optimal solution might be. The example we have here is in the vertical case, we have the prediction from neuronal networks. Our objective in minimizing this is going down and to find the solution that's down there in this graph. And in the horizontal axis, we have a ensemble of solutions performing the same way as the original sample. And the exploitation is on the opposite side. It is grouping this in this region, spatial region, to get the solution that we expect to be there. So this convergence ratio, it is grouping solutions, and from the exploration we go up to exploiting this or using this in this region of the space. We might have local optimal values. We have identified the promising regions, but we might be wrong, and we're finding from the local optimal solution, which is the local solution that's optimal, but we might not be finding or looking it at the right place, for it the right byte. Each byte is represented by a gene. We have a byte stream, and this byte stream is the genetic load, or the string of genes we have. We have then 10,000 up to 200,000 bytes, and the chromosome means here population. We have here per blocks. We have to have different optimal blocks differing per position. We have the possibility of crossing genes, having a cutoff point, and having multi-cross points. We could have several cross points. What we do here is dividing the solutions in blocks. As perturbations or modifications were introduced, disturbances, because the limitations are that optimal blocks will differ per section of the file. So we optimize per block. We do not break blocks that are already formed. But the problem is we might have big solutions. Solutions are too big, and because of the fact that we have lots of bytes, a lot of genes, that means that optimizing this is, to be in an acceptable period of time, population should be smaller. So we have 50 solutions as populations. We cannot find all the points thanks to cross points. Then we would need as many solutions as the number of bytes, says the speaker, as the possible variants of a block, the bigger size block introduced. If we had introduced 10 bytes, we would need 256 by 10, 256 multiplied by to the 10th. It is like we see here, it is this enormous figure with 10 to 240, and it is enormous solutions, enormous amount of solutions. If we had introduced 1,000 bytes, we will have an enormous amount of solutions. What is the paradigm? We have here high mutation ratio to reduce convergency. And here we have here that we reduce mutations and reduce genetic load. We introduce mutations with a high ratio and probability, and we disseminate solutions this way to talk about intuitively. Our objective is to write modifications in the file and to get pointing, to get scoring, and to move on to the experimental result. What he's talking about, we don't know what you're talking about anyway. And we see here that you're falling asleep. Yes, I realize. Anyway, well, what have we done here? We have established malware detection techniques based on artificial neural networks, and they say this is the best. Is this bad? No, that's good, but there are possibilities of mistakes. We've analyzed the state of the network and approaches, and we've proposed another method allowing us to create examples for a case to assess how robust the technique is and to enhance robustness of the samples created that are evasive samples. And then, how about experimental results obtained? Let's go on to the subject now. We have here the original sample detected. We introduce modifications, perturbations, X size, and then we enhance them and we compare this with the neuronal networks, iterating. If we cannot find a solution within an acceptable period of time, we have more perturbations, more modifications, and we give it a try again till we find an acceptable period of time for a solution. 50 generations, 100 generations, it depends on the improvement ratio we want to have. It's variable. And the data set used here, it's 2,260 samples, detected 100% of malware prediction, and the average is 0.96. Standard deviation is 0.07, and the median 0.99 for many samples. It's almost 100% sure they are malicious samples. If we detect this with virus total, for instance, you all know the total is 2,245 samples. I only got one not detected in virus total. Undetected, it is half a mega, but it varies from one sample to another. We have here prior, and what about after? We have 1.67% of detection. The first case 100%, and the other case 1%. 40 out of 2,260 are still detected. The average value 0.39. We said that from 0.5 I would say it's divided, but if I am an attacker I want to minimize this, and I would say till I have 0.01 detection rate I won't stop, and I get my evasive sample. We have an evasion that's 98.23%, 2,220 undetected samples, evading samples. And then we have a problem from the beginning, which is FOC, so to speak. We have an enhancement of the cases. And I say this is not a problem. Why is it a problem? Why is it not a problem? Because we have here the size of the modifications, mean value, average 5.14%, deviation is 10.81%, median value 0.98%. We have evaded with less than 1% of size increase. It's good. And let's zoom in, and we have here that we have evaded 1,335 with less than 1% of perturbations and modifications. Perturbations introduced are very small, almost neglectable, introducing less than 1% of modifications. And to say it's going to be mapped, it's excellent because you have access to the source code. What happens with the time? 10 minutes for finding evasive sample. But if you have the median value, it is only 4 minutes. If you have a standard deviation that's wide, it's broad, that's good for two reasons, two different approaches. On the one hand, we put a black hat and we have a sample, and we do not want to be detected by a neuronal network as a target. Mean value, 10 minutes to wait. I have to wait for 10 minutes. That's not important, neglectable. You're not wasting time. But if we have now the other hat, we change hat. I'm good. I'm wearing a white hat. So I want to enhance robustness of the system. 4.4 minutes, that means that for half of the data you have an evasive modification. You can stop after 5 minutes, and we're generating evasive samples to retrain our neuronal network. If we look at this, if we look at the bytes introduced, look at the histogram, the bar chart here, we see it's quite uniform. It is like 120,000 times. So we have a restriction that there was no byte better than other bytes. It is according to blocks. That is why we have decided to have a block approach, cross points according to bytes. Byte 0, it is here quite common to see, commonly found, and the trash bytes for padding and imports and so on, whenever prior to getting into memory and so on. So we're going to show you video and demonstration. Let's look at it and let's see how it works. And what we're going to do is, we have a sample here, original sample, and we have a hash, and we're going to copy it. We're going to name it modified sample, the one we're going to modify to compare those two. And then, to make a long story short, if we have let's see, prediction given by Malcolm of the two samples, it says 96%. They're sure that those are malicious samples. Malcolm architecture, it is the entry layer and the embedded layer, deleting the next values, convolutional values, and those densely connected layers. So we're going back to the prediction, and parameters here are 1,043,000 almost, 1,043,000 characters, and it will launch the algorithm to get the evasive sample from the original sample. You will see down there on the right hand side that the size will vary. We're going to enhance the size. We'll have some artifacts. It is not to modify the original sample, and that will be deleted at the end. So we load the neuronal network, we insert modifications in the binary file, and we have the evasive sample. We have a prediction, initial prediction here. We started with less than 1%, and we see it's been enhanced 1 kilobyte. So I have inserted 1,000 bytes. It is less than 1%, nothing almost. No, it's neglectable. If I ask Malcolm to give us the prediction of the two samples, we see the modified sample there. You see the size has changed. It's 0.36. It's only 36% sure that this will be malicious, less than 1% of modifications introduced. So it's a malicious 36% of probability of having a malicious sample, according to Malcolm. If we launch this deep analysis, and it's a standard, de facto standard, to see two binary files and compare them, they match up to 96%. They are 96% similar. If we introduce less than 1% of modifications, they compare blocks. If I introduced modifications in different parts, they will give 99% of similar values. If we look at this and we see here, for instance, the selection table from the two samples, we can observe that, obviously, as a matter of fact, the memory address, the memory size, entropy, and the hash from different sections are identical as it is the disk space. It's been modified not to be mapped. The introductions are not mapped in memories. So the execution is like the original one, exactly identical to the original execution. So, conclusions and future work now. Conclusions, summary. What have we done? We have established the generation of examples allowing us to have the assessment of malware detection systems. We have reached 98.23% of evasion rates, and we've got functional results. You can be asking yourself, are those functional results? Yes. We had the modified sample, the normal sample, and they behaved exactly the same. The only thing you have no access to the source code. The source code is that the malicious sample can check his own integrity, but nothing happens because from the attacker viewpoint, and the time necessary and the introduced modifications are small. Viable attacks, and the defender can improve techniques, retraining neuronal networks. If there is a problem, you will see it's difficult to detect. As conclusions, deep learning models are not the final solution, but they're useful whenever they take into consideration their weak points. We have to consider their weak points to be considered, but they can be evaded. We also think we should demand the assessment of how robust they are. The way we have detection ratios and false positive ratios, there are ways to measure how robust they are. For the future, we would like to have different approaches as the ones we've been seeing, and to compile different models and to put one on top of another, to have different architectures, stocks of architectures, to see if we can divide the whole thing, or in the end they are enough, they are robust enough, and we have to assess the effectiveness and efficacy of the retraining with the sample. We have to finish this to publish the paper. I'd like to make some statements on what has been said by those two data scientists. It's from Sophos, the antivirus company. The one asked, how do we defend against adversarial subversion of security models, and how could we imitate those evasion mechanisms? He said that the best thing is to add different layers on top of each other because it is more difficult to evade everything. Richard Lang said that obviously the best return from the investment is when you put on top different models as a stock of models, but models should be the best possible models, one on top of another. And to do this, one of the main techniques is adversarial training, as we have proposed.
So this is the end of my presentation. Thank you very much. Thank you for your attention. I hope you've learned, and we've learned something from the presentation. If you have questions or if you want to talk about this, I'll stay all day long here, or you can write to me, or shoot me an email, or write on Twitter. Thank you, Javier, and congratulations on your presentation. Now, is there any question from the audience? Thank you for your excellent presentation and for the wonderful job you did. You said wire hackers can generate samples or patterns every 5 minutes and upload them in the neuronal networks. One of the problems of neuronal networks is overtraining. I don't know if you tested overtraining of neuronal networks in order to see when the detection degenerates. No, we didn't test this because the idea was to assess robustness and to generate samples to retrain the network. The second part of the job would be, as you mentioned, to use evasive samples and retrain the neural network, which poses problems because retraining will make the network more robust and more evadable, or they are more robust, or you can end up with an infinite cycle. They are more robust, less evasive, and so on and on. But I think it's a future job, and it's a future research I would love to conduct. Any other question? No more questions? Oh, yes. Thank you. And first of all, I would like to congratulate you on your very interesting job. I have a question concerning traditional antivirus. You mentioned how when you modify the original executable, the detection ratio of neuronal networks go down. But what happens with traditional antivirus? Do they stay stable? Is it maintained? Good question. One of the things we wanted to do is after modifying we wanted to compare against Veros Total. So to what extent we break signatures in order not to detect samples, a lot of work has been done, and let me tell you that no reduction was detected. But I cannot talk to you further because we are completing our job, so I don't want to disclose any information that is being considered at this point in time. Sorry. Congratulations on your job. If I understood you correctly, a semantic verification of headers to check disk addresses don't leave loopholes. This will make the methodology to be outside the neural network, but is detected. Yes and no. That's one of the problems I said at the beginning. One is not detectable, one is easy to be detected, but we are working under the restriction because we have no access to source code. So if you want to get evasive samples to increase robustness, this does not pose a problem because headers can be detected. From an attacker point of view, if you have access to the source code, you map, you insert modifications or disturbances, you map in memory, and then the sample will be functional with the modifications introduced, even if it is not detected. So the question is not, from an attacker point of view, it's not detectable. Yeah, we have time for more questions. No more questions, so thank you, Javier. We'll continue here within a couple of minutes. Thank you.